So how do we interpret the parameters of a logistic regression? Okay, so for quantitative explanatory variable, right, we are looking at the marginal effect of this explanatory variable. So again, if we look at the model, all right, this probability of y equals to 1, I'll just denote this as pi. As what you have seen before, it is this form, all right, e to the z over 1 plus e to the z, or e to z plus 1, all right. What is z? Z is this one, the index as we referred to as this, all right. Now, if you differentiate this with respect to your x, okay, you will get this thing here, all right. So you can do the math, all right, just do the calculus. If you differentiate this, you will get back this, okay. So you will find that this marginal effect, okay, this is a constant. When you estimate it, you will get one number, but you will find that this p, all right, which is this, okay, which is denoted, which is given as such, and therefore 1 minus p, all right, the value is dependent on your x, okay. So usually what we do is we find that the marginal effects, okay, if you want to find, just get one number, although you know that the marginal effects are not the same because it depends on what each of these x values are, okay. Then what we do is, usually for reporting purposes, we just compute the marginal effect at the mean, we said. At the mean means we find all the x1 mean value, x2 mean value, xk until sk mean value. So we just plug it in here, all right? So when we plug it in here, we will get our z at the mean. And then to find pi, this is going to be e to the z at the mean. This is e to the z at the mean plus 1. So we will get just one number for this at the mean. And then we will also find this 1 minus p, all right? So this one has no subscript and this one has no subscript. So we just find the p value at the mean values of your x, okay? So as we said before, the p value is computed at the mean values of the explanatory variables, right? So this is in comparison to the LPM. For the LPM, if you differentiate this function with respect to x, you're just going to get the beta, all right? Whichever beta, if you differentiate with respect to x1, you're going to get beta 1. If you differentiate with respect to x2, you're going to get beta 2. So it's just a constant. But for logistic regression, you find that if you differentiate with respect to any of these x, all right, this is not constant. So if you look at it graphically, your LPM, okay, is a straight line. So the marginal effect, the slope is always the same for this red line, okay. But for your logistic regression model, okay, you find that the slope is not the same. It depends on what this x value is, all right. For low x values, the marginal effect is very small, all right. But when you reach a certain value for your x, you find that there is a jump in the probability values, okay, in the probability that y equals to 1. So here, all right, if you look at this logistic regression model, this is more realistic compared to your LPM. Okay, so for dummy variables, all right, so dummy variables is a little bit tricky, all right, so you cannot differentiate the function because it doesn't make sense. So what you want to do, okay, is that first of all, right, you compute this, your index, your z, all right, when d equals to 1. So put d equals to 1. And then here we're assuming d is either 0 or 1, okay? And you have only this one dummy variable. Of course, dummy variable has either 0 or 1, but we assume that we only have, this to represent a qualitative explanatory variable which has either, which has only two outcomes, okay? Just to make it simple. So over here, all right, so what you want to do is you compute this z value, your index, because you want to compute this, you need to know what your z is. So for your z, okay, once you estimate it, estimate, you will get this beta naught hat, beta 1 hat, beta 2 hat until beta k hat. But if you want to compute your z, you also need to know your x values. So what you do is, you put all these x values at the mean, okay, at the mean value of your x. So here your d equals to 1. So find that, right? So find the probability of y equals to 1 when d equals to 1, and then do the same, when d equals to 0, again at the mean values of x. Okay, so you find probability of success y equals to 1 when d equals to 1, and probability of y equals to 1 when d equals to 0. Okay, so when you subtract these two, this will tell you the difference in probability of success between group d equals to 1 and group d equals to 0. Okay, so for example, if your d is equal to 1 means male and d equals to 0 for females, then suppose you compute, right, based on what we have said here, and you compute that probability of y equals to 1, okay, given for male is 0.15, and you do the same thing, all right, when d equals to 0. So, and you do that and you get 0.4. So we find that when you look at the probability of success for female is higher than for males. So we can say that females are more likely to be success, right, compared to male. In this case, it's more than twice as likely because 0.4 is more than twice of 0.15. Okay, for probit, or what we call sometimes the nomit regression, most of the time we refer to this as your probit. Nomit because it's normal. Okay, so probit regression. Now you have the probability of y equals to 1, right, is your cumulative standard normal. Okay, so this is not, as we said, a closed form. Okay, so we have over here like this, and recall that this is your phi, all right, of your z. Z is your index here. We have this, okay. So just as a comparison, your logit model, okay, the probability of y looks like this, okay, whereas for nomit, the probability of y, it looks like this, okay. So it looks somewhat complicated, but actually because we have the statistical softwares to do the computation for us, so it is not as difficult, okay. Now again, as we said before, this is your standard normal PDF, okay, and this is your CDF, your cumulative distribution function, which is just the integration of this PDF, okay. So if we want to look at the marginal effect for the quantitative explanatory variable, okay, if we differentiate this, okay, function with respect to one of these x, okay, you will get it to be equals to beta j, right, phi of zi, right. So basically what you want to do is find what is z of xi. So again, all right, you find that this one here, all right, is not constant because it depends on the x, all the x values that you put in. If you have for a dummy variable, right, you do the same thing as how we do it for the logit regression model. So again, you compute this z for d equals to 1, and for the rest of these x values, all right, you put it at the mean, and then you find, all right, what's the probability of y equals to 1. You just find the integral of this. You can actually do it in Excel even, okay. So you do also when d equals to 0, so just plug it in, d equals to 0 and the rest at the mean values. Then you find the probability of y equals to 1 when d equals to 0, and then the difference, right, would just be the difference in probability of success between the group d equals to 1 and the group d equals to 0. When we are dealing with probability models, we can also talk about, the goodness of fit measure. Instead of the R squared that you have seen before for the regression models with quantitative dependent variable, for your probability models, we can have what we call the count R squared. The count R squared is just the ratio of the number of correct predictions divided by n, your total number of observations. So if you make all the predictions to be correct, then it's going to be n over n, which is 1. If your predictions are all incorrect, then you are going to have 0 divided by n. Okay, so how do we find this measure, this count R squared? So we have any of the predicted probability which is greater than 0.5, you will classify it as 1, right? And any of the probability which is less than 0.5, you classify it as 0, okay? So for instance, if we look in this table, you have, let's say, many observations, all right, 1, 2, 3, and so on. And suppose the actual y value, right, is 1, 1, and 0. Let's say you are talking about, let's say, whether the person bought a house or not. If bought a house, will be 1. If did not buy a house, 0. So the first individual bought a house, 1. The second individual bought a house also, so y equals to 1. And the third individual did not purchase a house, so you will have 0, and so on. Okay. Now, when you do your estimation, either you use your probit or logit. Suppose when you estimate this probability of y equals to 1, you get it to be 0.8. For the second person is 0.4. For the third person is 0.3, and so on, right? So you will classify this to be 1 because the probability is greater than 0.5. So 1, this one will be 0, and this 0. So which means that for the first individual, according to your estimated one, you predict that, all right, the person will purchase the house because the estimated probability is more than 0.5. So, and the actual value is also 1. Therefore, your prediction is correct. Okay. For the second one, you predict that this individual did not purchase a house, but the actual fact is he or she did purchase the house. So your prediction is wrong. Okay, and you can do the same thing. For instance, for the third one, right, according to your estimation or prediction, the individual did not purchase a house, and then yes, the individual actually did not purchase a house, so your prediction is correct. Okay, so what you want to do is find what is the count R squared. Okay, so this is one measure of goodness of fit, but when we are dealing with logit or probit model, this measure of goodness of fit is actually of just secondary importance. Okay, so it is not the main thing that we're looking for. You can report the count R squared, but that's just about it. Okay. We can also conduct tests for overall significance, like the usual, models that we have, which is the non-probability models. For probability models also, we can do the test for overall significance. So the test for overall significance is as what we have, H naught, all the slope coefficients are all 0. For the alternative is at least one of the slope coefficients not 0, all right? Some of it, okay, not 0, some or all, or at least one, we said. So the test statistic that we use is a chi-squared test statistic, which is equal to -2 times the log of the likelihood function, all right, under H naught, and the log of likelihood function, which is unrestricted. Okay, so you can, over here usually we don't manually compute it ourselves. This will be reported whenever we use eViews or some other softwares. All right, so you will have it is equal to this. Okay, your critical value is just going to be your chi-squared at your level of significance alpha and the number of explanatory variables that you have. Now, if you find that this chi-squared value is a large number, you will reject H naught. It means that you have overall significance. Okay.